I'm writing prerequisites, but this is virtually not not of anything fancy is not required. So obviously, I'll be needing you to know when you add things and when do you multiply. Add slash multiply. Uh, no, I have this Meet open also, right, side by side. So I can't really make it bigger, just so that I can see the chat and all. Because you guys are not willing to speak up, I have Meets open side by side. So I can't really make it larger. Sorry. Right. You would need to know that. You would need to know definition of injective, bijective, surjective. If you don't, quickly Google. Also, I think you can just hide all like people, right? Something like that, or like reduce the number of people that are visible. Right. You need to know this, and you'll need to know like some basic properties of them. Like, when can you say that? Right. You'll need to know some basic properties, like when can you say that, like injective and surjective together imply bijective, or when there is a set of size like two sets of finite size have an injective function between them, the function should also be bijective. Basic properties like that, I would expect you to know. And the third thing I would expect you to know is like what permutations are and how to count them. Permutations and factorial. Okay. Right. Oh, I'm just saying injective. Let if A to be injective such that uh, size of A equal to size of B less than infinity, then F bijective. Something of this form, I would expect you to know. And I'll not be proving things like this. Okay. Like when something like this comes up, I'll just assume it. And if you don't know, then you should try to prove these results as we go along. Some precautions. Could you give some basic? I would recommend that you take 5 minutes and just quickly Google rather than me explaining. Because yeah, I would like to go on to other stuff, and then like you can take 5 minutes. It's not a bother because I'll be just writing some basic things only. Okay. At no point in the lecture should you tell me that n choose I is equal to n factorial upon I factorial minus n minus I factorial. At no point shall you use this. At all point, and all that n choose I means is that you pick I objects from n objects. That's it. I'm not asking you to use, at any point, you're not required to use any of these values. You're not supposed to tell me that, oh my God, we do this, a plus b to the n is equal to summation of a to the I n minus b to the I n minus I and choose I, blah, blah, blah. No things like that, at no point should they come up. If you are using summations of these coefficients, give me a combinatorial interpretation. I'm not into these calculations. Okay. You shouldn't use generating functions, polynomials, nothing of that sort. Okay. Everything n choose I, all it means is you pick I objects from n objects. Nothing more.
Okay.
Cool. Is this fine?
Yeah.
All right. Cool. So let's start with some summations that you have all seen before, and let's see if you know how to do them. You guys have all heard of this I summation of I equals 0 to n of n choose I is equal to 2 to the n. How do we do this?
So we have n objects and we have to choose like I objects. So it's like you arrange all the objects in a line, and then there are two ways that you choose the object or you don't choose the object. So two ways
Okay,
for one object and n objects, so 2 to the power n, which is equal to the left hand side. Like n
cool.
choose 1, n choose 2, so on. So like that.
So this is just telling you can pick any number of objects. Like you can pick either 0 objects, or you can pick one object, or you can pick two objects. So all this left-hand side is telling you is you have to pick some objects in some way. Now, out of n objects, pick n. So if you have n objects, with each you have the choice, pick or not pick. So how many ways there are? 2 to the n. So we get this summation. Okay. School will tell you this comes from 1 plus 1 to the n is equal to 2 to the n. They are incorrect. That is correct, but you shouldn't use it. That's not how. That's not like the interpretation you should usually go for. Of course, it will be useful, but not for now. Okay. Another standard thing that you would have seen is summation I equals 0 to n minus 1 to the I and choose I is equal to c. How do we do this?
Oh, this is like previous. And when we have mm, odd, then we get minus, so cancels. Like in the
If we choose
previous.
a object, then we
And
should not
also,
choose the consecutive object.
yeah, yeah.
Sorry. Can you repeat? Any one of you? Uh, I literally just told you to not get into this kind of thing. What's the
So what
combinatorial?
what I was saying that like in the previous number one, here we have just minus one. So when n is odd, we have minus one. So those will cancel, and we will get zero.
What do you mean when n is odd? Oh, yeah, but like, why should the number of ways of
Because
getting odd
uh,
things
because
be?
because like n choose I is equal to n choose I minus I.
Yeah, but like n could be even.
Oh yeah,
Also, try not to use those kinds of arguments. I want you to get a good interpretation of this.
yeah, yeah.
No. N could be even, so then that argument won't work. Anybody?
For odd, like it was key if you have n objects, so the number of ways of choosing I objects and not choosing I objects, something like that.
No. What is this? It was like this.
No, no, I mean like we can do like this, but that doesn't work for even. I haven't seen this before for this one.
Okay. Okay. Sure. The argument does not care whether it's odd or even if you're doing the right argument. Okay. So what should the value be of if you just considered the odd ones, or if you just considered I even? What should be the summation of, like, let's say I even? Uh, what should be I equals 0 to n and I even of n choose I. What should this value be?
Number of ways to choose an even number of objects out of n objects.
Good. But what should this value be from this statement? That the number
Ah,
of ways of doing odd objects and the number of ways of doing even objects is same, and you know both of them sum up to 2 to the n. So what should it be?
or 2 to the power n minus 1.
So that should be the answer that you're going for. All you want to no, 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 no. It is not 1 plus x to the n because we don't know how to compute binomial coefficients.
Yeah, we don't have to use it.
That is one thing I told you at the beginning. We don't know binomial coefficients. No. N choose I is number of ways of choosing I things from n things. That's it. Okay. So we want to prove this. We are on, I mean, if you reached 11th grade, then you should be able to do it with stuff less than 11th grade, right? Pranav?
Yeah,
There's no,
exactly.
Do you just ignore last element and then pick the remaining ones, and then this one exists or it does not, depending on parity of how many you choose?
exactly. Perfect. You ignore the nth element. You just consider the first n minus 1 elements. Now, if I've chosen some selection of them, let's say, then the option whether I choose the last one or if I do not choose the last one is forced on me because of parity. I do not have any option. Like if I've chosen an odd number of things till now, I'll need to pick it. If I've only chosen even number of things till now, I'll not pick it. So I'm done. There are 2 to the n minus 1 ways of choosing the rest of the objects. Same argument goes for odd. If I start by choosing any of the n minus 1 objects I have till now, if I've chosen even objects, then I have to choose the last object. If I've chosen an odd number of objects, I don't choose the last object. And that's it. Okay. Does that make sense? Yeah, sure. So the point is, the question is telling you that if you pick an even number of objects from n objects, there are 2 to the n minus 1 ways of doing this. So all I'm saying is, I only look at n minus 1 objects, and I take any choice of them. And if you pick some set of the first n minus 1 objects, the choice of whether you pick the last object or not pick the last object is forced upon you. Like if I have chosen an odd number of objects till now, I will have to pick the last object, right? Because I want an even number of objects. And if I've chosen an even number of objects, then I don't choose the last object just because that will end up with me an odd number of objects. And that's bad for me. And that's it. That gives you the answer 2 to the n minus 1. And similarly, you can do it with I odd.
Like, do we need I odd? Like, after I even, we're already done. No?
Yeah. I'm saying like if the point was to just calculate this value with I odd.
Yeah, okay.
Okay, so another thing that you might have seen, third summation. Summation of k and choose k. I can start, don't worry, we'll get to hard problems soon. The ones who are like, oh my God, this is too easy.
And it's you count the number of times an element is in a subset, right?
What?
You know, count the number of times an element is in a subset. That's what this is.
Okay.
So it's an n2 to the n minus 1.
Can you repeat? Like, what do you mean by count the number of times an element is in a subset?
So if an element a set from 1 to n, the number of
Mm-hmm.
times 1 is in any subset, and then the number of times
Okay.
2 is in any subset, the number of times 3 is in just double count that. This is one way, and the other one of the way would be the other way.
Right. Okay. 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 Yeah. So you're just taking any subset and marking a special thing,
Yeah.
right?
Yeah.
Okay. So right. Perfect. So we will. What Siddharth is saying, I'll rephrase into a different interpretation. You have n students in a class, okay, and you want to pick some of them to form a special council, okay. In that
And to
special
make the
council,
president of one of them.
and you want to make one of them the president, whatever in that special council. So if you were choosing k people, you will have k choices for the president. So your answer, so number of ways of doing this with k people would be k into n choose k, if your council was k sized.
Yes.
So if you were doing arbitrary size council, it will be summation of k choose n to k into n choose k. But what you could do is you could pick the president of the council first. And that would be, you pick the president. There are n ways to pick the president. And rest of the people, how many ways to pick? 2 to the n minus 1. Good? Make sense? Okay.
Yeah.
So this is the kind of arguments we want to do today. We don't want to use values at all unless necessary. Until we don't have options, we want to minimize the amount of algebraic things that we are doing. And we want to just get good interpretations of everything as much as possible. Okay. Not being that unreasonable, am I? Okay. So let us start by introducing something called permutations. So we start with this problem. Let's say you have n people and you have this huge dining hall. This whole area is a dining hall. The n people are lined up outside. This is person 1, this is person 2, person 3, person. Now person 1 comes in. They see that the dining hall is empty. They're like, I want to sit. So they take out their magic wand and conjure up a dining table. So now there's a dining table. And they sit here. Now the first person is gone inside and there's a dining table. Now the second person comes. They can either, yes, and a chair. Yes. Now the second person comes. They can either be like, I'm very good friends with the first person. I'll go sit with them. Or they can be like, yeah, I'm feeling like I want to sit alone on my own today. They can conjure up their own table and sit there, or they can go and sit with the first person by conjuring with just a chair. Yes, magic is completely fair. Come on. Magic is always allowed. Now the third person comes in. Third person has more options. They could come in and they could either sit with this person. Okay. They could either sit with the first person in between these two people, or here, or even here. Okay.
What are these boxes you make?
Oh, chairs. They're just chairs.
So how many chairs are there?
Oh, you just come up and you wave your magic wand and you make up a chair.
Okay.
And you put it anywhere you want. Like they could be
Okay.
like, I don't like these people, I want to sit in between them. Or they could just go and sit on the opposite side. Or if there was a second table, they could be like, I want to sit with the second person instead of the first person.
Like each person can also get their own table also, right?
Yes, they can be like, I don't like any of them. I'll just make my own table. That is also a fair option. Okay. Right. So the question now becomes, how many ways can these people be sitting at the end of the day?
N factorial.
Wait,
Good.
what's the question?
How many ways could they be arranged? Like how many ways could these dining tables be arranged? Go on, Atul.
Like you can either look at it as first guy has one choice, second guy two choice, or like
Okay.
you can look at
Does
it
the
as
arrangement of seats in a
cycles
table
of
matter?
Sorry, can you repeat?
Does the arrangement of chairs in the table matter?
It matters up to rotation. Like in the sense, like if it's just the same people with like and the table is rotated, then I don't care. But if like ordering of people has been changed, like it instead of 1 2 3 it's 1 3 2, then I care. It's
Yeah.
different. Okay, Atul, give me a different answer. Like not one where you're directly counting it. You can't directly count it, but don't do that.
like write the permutational cycle notation or something.
Perfect. Somebody else.
Okay, so this is just the number of permutations.
Yes, yes. Can somebody else explain to me why?
Suppose like we are to like kth person has to go, and there are like k minus people like who have gone before him. So we write okay, a people are sitting on the first table, b and this, and like we count the number of options directly. Which
How?
comes out to be.
How do you count?
I mean, like there are a people on the first table, so there are a options only, like between which two it will sit, and then a plus b plus so on. So there are k minus one plus one option that he can create a new table of it.
Yes, good. That is one answer. And create a bijection with permutations, the number of permutations you're saying, right? Like let's not say it's n factorial. Let's just say that we want to show that it is a number of permutations, whatever that is supposed to be. Let's say we don't know that it is n factorial. Like we just want to show a bijection with the number of permutations. How do you do that?
What do you mean by number of permutation? Like kiska permutation?
Let's say we don't want to count it, but we just want to show that this is in bijection with the number of permutations.
Like what is in bijection? I'm asking.
The number of arrangements
Uh-huh.
is in bijection with the number of permutations. Like the set of arrangements is in bijection with the set of permutations of n people.
Each person just goes to the next seat clockwise or something.
Yeah, perfect. Perfect. So I just look at who's sitting to the right of me. If I'm sitting here, I just look who is on the right of me. This might be another person, or it might just be me. Okay. So I write f of I as the person to the right of me. So to the right of I. This gives you a permutation. Yes. And every permutation can be written this way.
What would do like if f of I is I? So like,
That is okay. That means they're just sitting on their own, no?
yeah, so like isn't like permutation you're saying if we arrange them in a line, so like using this function we can create a bijection between these two cases.
Permutation is like just arrangement. Yes.
Yeah, so like basically we are trying to relate this situation with a situation where n people are on a line, right?
Sure, sure, sure.
Yeah, so if I say like on the first table p1 p2 are sitting, and on the third table p3 is sitting, second table p3 is sitting.
Sure.
And on the third table, P4 is sitting. We have 4 people. So what will be
Okay.
like its correspondence there? Like P1, right of P1 it's P2, and
Yes.
on the right of P2 it's P1.
Sure.
So it's a cycle. So like how do we arrange them in a line in that way?
I mean, what is a permutation? Okay, tell me what a permutation is.
Arrangement.
Okay. So when I say f of I is something, that's saying that if I was in some spot, I take it to the f of I spot. So if f of 1 you're saying is 2, then I just place it into second spot. It becomes 1. If f of 2 is 1, I just place it here.
Okay,
If you're looking at as that interpretation.
yeah,
But
yeah.
otherwise permutations are just bijective functions from 1 to n to 1 to n. Nothing else.
Yes.
Okay, good. All right. Is this clear? This gives you all permutations. The why I'm saying this is very important to understand. So this cycle notation. This is called the cycle notation of a permutation. Just you say I goes to f of I, goes to f of I, and so on, and you eventually get back. This is called the cycle notation of a permutation. This is a very important thing to know. Okay. F should be bijective to be a permutation. That is, it's equivalent. F
Yeah,
a,
yeah.
bij
Yeah,
a
it's quite
bijective.
equivalent. Like you said, just showed.
Yeah, yeah. Okay, is this much clear? Cool.
Yes.
All right. So try this. A simple problem. Second case is if you have 1 to n plus 1 and you want to create a surjective function to 1 to n. How many ways are there?
So we first pick like uh, the first n elements. Like let's call 1 to n plus 1 as set A and 1 to n as set B. So we pick 1 to n from set A, and they should go to at least n minus 1 elements in the set B. So if they go to exactly n minus 1 elements, then what do you say that n plus 1 is forced in the nth element. And if they go to n elements, then n plus 1 can be anything.
Sorry,
So
can you repeat?
okay. So we first consider 1 to n in the first set. Let's call that A. And they
Okay.
should go to at least n minus 1 element in set B.
Okay.
If they go to like exactly n minus 1 elements, then n plus 1 is forced to make it surjective.
Okay.
And if they go to n elements, then n plus 1 can be anything among these n, right?
Sure.
So now let's call the number of ways here as an. So it will be like an equal to an minus 1 plus the number of permutations of n objects times n. So n times n factorial, I guess that will be. Yeah.
This is tiring. I'm not doing recurrence. How will I
Just pick
solve this?
permutation of 1 and 1 to n plus 1 and remove the thing with n plus 1 and replace it with one of the others.
What?
Like just pick a permutation of 1 until n plus 1. There's
Okay.
something assigned to n plus 1.
Okay.
Delete it and assign it to something else.
What is something else?
Any of the other n things.
And how is that a permutation?
No, I mean you pick a permutation first, and the thing assigned to n plus 1, you assign it to something else among the first n.
Good. Yeah, that is perfect. 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 Yeah. Does everybody understand that? Okay. Follow up, Atul. Do you overcount?
Yes.
I don't want to overcount.
Like you just divide by 2 or something, right?
Yeah, do it directly. I know that your question, you will get the exact value that we want, but let's not bother. Okay, the point is you're sending n plus one thing to n things. So one of the elements has been counted twice. Perfect, Rishabh. Explain, please.
You can choose 2 elements from n plus 1 to
Yes.
map to the same element, and then you can just permute the rest.
Perfect. Pick 2 elements. Oh, man. This one. That will go to the same thing. And then you just have n factorial ways. Answer becomes n choose 2 into n factorial. Sorry, n plus 1 choose 2 into n factorial. Okay. All right. Okay. Is this much clear?
Yeah, clear.
All right. So try this problem. That let's say you have n plus 1 elevator, n plus a building. In fact, it's n plus 1 choose 2 into n factorial. Yes. So you have an elevator which has floors, like you have a building which has floors from n minus 2 till floor 0. Okay. And you have an elevator that starts at the nth floor. Because you are a weird mathematician and a student of mathematics, you're like, let me be crazy. And you decide that you want to, like, you want to be like, I just want to get to the 0th floor. So I always want to keep going down. But I want to press buttons randomly. So you just start. So you first start by picking any random number from 0 to n minus 1, like with equal probability. And you pick some of them and you reach that floor. And again, you pick, if you are at floor K, you pick a lower floor randomly. And you keep doing this. How many ways of reaching the bottom?
You can again form a
Why is the
rectangle.
probability relevant?
What?
You said you pick with equal probability and all.
At each step, you pick with equal probability, yes.
Like that's not relevant if you're just counting a number of ways, right?
Sorry, I mean, find the average number of elevator rides is the follow-up question. Like, obviously, that is the first question, but there are follow-ups. That's why the probability matters.
For the number of ways, we can still make a reference. No?
Okay, so number of ways you'll recur.
Yeah, so at n floors,
No. It's fine. I'll just be like, Pranav will recur. Pranav is doing his own thing. I don't care. Okay. Yes. So now the question is average number of elevator rides. And then the question becomes,
Okay, so we can do like this for the number of ways. We consider
average number of second last floor. Like last floor is 0, but what is the average number of the second last? Okay.
What is that
Go
number?
on.
Average number of second last floor?
Like we are going to each floor with some probability, right? So
Okay.
each each way of reaching to the bottom has some probability. So what across all these probabilities, what is the average number of the second last floor?
Yeah. So like for the number of values, we can consider like a permutation of the n numbers, and we pick the decreasing sequence in it, the largest decreasing sequence, let's say, and then we choose any k elements of it.
Don't you just do like 2 power n depending on which lifts you, like which floors you stop at?
Exactly.
Okay.
2 power n minus 1, but yeah, like these are n minus 1 floors.
It's 0, right?
I mean, 0 you have to just go to.
Oh, fine.
So these n minus 1 floors, you have, do you stop at this place or not? So 2 to the n minus 1 probability. Yes. Right. It's okay. Happens sometimes. Right. So this is something that you have to think about. I'm not going to be talking about this. Okay. This is just a question for you guys to try on your own.
Okay.
Okay. Let's say now try some problems from contests. Okay. What is whatever you're saying, just say it. I can't open chat. Too much effort.
Like, is there exist like nice combinatorial argument for them or
Of
manipulations
course.
in
No.
for the follow-ups I was asking.
I mean, I wouldn't give you if it was not nice,
Sure.
or if I did not believe it was nice. Let me put it that way. All right. So contest problems. So do you want to start from the IMO, EGMO, or some national contest? Of course, you guys want to start from the IMO. Okay. So do you know what a fixed point is in a permutation? Sorry, we have gone to the IMO now. Yes. So number of points, a fixed point is any point that maps to itself. Okay. So for k, like, okay, you're given an n. Let p of k be number of permutations with exactly k fixed points. Okay. Yeah.
Okay, so we can first find P of K.
Have you seen?
Nailed
How,
it. I
okay.
haven't seen that.
How do you find p of k?
Yeah, so we like there are n elements. So we first choose the k elements which are fixed. So
Okay.
n choose k, and there are n minus k elements. So n minus k factorial ways to permute them.
But you've also counted the other ways.
Oh, counted the.
You've
You have
also
derangements and then minus k, which is not nice.
Oh. Yeah, fine.
like you've also counted like k plus 1 and k plus 2 and so on. And if you do this again, you'll count way too many times.
Oh, so we can do like for k and like first fixing k points, and then the number of permutations of that will give like k plus 1 so on, and then we can do same for k plus 1 and उन्हें subtract कर देंगे तो k का आ जाएगा.
No, we have counted the number of permutations with k plus 1 multiple times. You have counted it actually k plus 1 times,
Yeah, finally.
but that is good. Your argument is not bad at all.
Um, just nck into n minus k factorial. So like n factorial by k factorial.
No, no, no. The issue is you have already counted the permutation. Like you're also counting the permutation with k plus 1 things. Because in the rest of the, like I'm saying p of k is with exactly k fixed points. So
Oh,
you're
right,
all,
right, 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 yeah. Makes sense. Fair enough.
yeah, yeah.
Oh, could we just use the cycle notation and like
Go
I don't
on.
know.
No, no, go on. Try.
So like say the n minus k points that we are not fixing, we just look
Mhm.
at all the possible cycles we can make with them. Like you can just relabel them to 1 to n minus k, and we'll just look at all the numbers of cycles that you can get with them, and that should probably do it. Like you can compose the cycles and all.
Okay, I don't quite see it.
Sorry, but I'll think of something else.
Sure, sure. This is not, this is good though. It's good.
Can you like fix an element and just look at how many times it is fixed? Because k p of k is essentially like
Shut
for
up.
each.
Shut up.
Fine.
Any ideas, others? Even if you followed Atul's argument. Good, good. That's for the best. Ah, bad. Atul, I'll send you some problem on private chat. Try that.
Fine.
Okay.
I kind of cheated. I mean, it's not cheating. Like I didn't do anything, but like you can sort of backtrack. No, key that pn has to pn plus one has to be n plus one factorial minus n factorial by n plus one. Like you just like consider this as a you just take the two, and if we take for n plus one, take for n, subtract and then divide to get pn plus one. And so can't we just induct then? Since we
Uh,
now have a closed form, we can just
didn't follow. Didn't follow.
no. Like we're assuming that the question is right. You can guess like a formula for pn, no?
Oh, no, 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 no. Please don't do that. No, please, no.
Oh no, but like the closed form is there only. Pn is just n factorial minus n minus one factorial
Yeah,
whole
that is
divided.
not. That is not correct.
4 divided by n. Okay, cool. I guess.
I mean, also, n minus 1 factorial is not necessarily divisible by n.
Yeah, no. Okay. All right. Yeah, sure. 10 is a prime. Fair enough. Oh,
There's a
right.
hint,
Yeah.
there's a hint attached, Atul, at the bottom. You might want to look at it or not. Up to you. Cool. Right. Gautam, you were saying something?
Yeah, I this doesn't seem to be working, but what I thought is, so this forms like a triangle, like if we write out everything. So like we'll do P1 plus P2 plus all the way till Pn, and then
Right,
next
right,
line
right.
P2. And then if we add like the missing terms, summation Pk from I to n, that should just be n factorial, the number of permutations.
You're doing this, right?
Yeah, and then completing the thing by adding the missing terms.
Yeah, no, no. Like this might work, but again, there's a very direct argument.
Okay. No,
Like,
I'm not getting this to work. Like I might be making a mistake, a calculation mistake or something, but this is what I thought.
Okay, what I mean is we have done this exact idea before today itself.
Yeah. In the n times 2 to the n minus 1 thing.
Exactly, precisely that. Gautam, that is precisely the correct argument. Can you
Right.
go through with it?
Just a second. Like we'll.
Oh, right. N factorial is the number of permutations of n objects, and then now you can just do like a case by case analysis. What if there's one fixed point, and then what if this?
No,
That's the
no,
element, right? What?
no. Why do you want to find what P of I is? Never.
I don't want to. I'm doing a double counting. Like
Okay.
the n to the power n minus 1 type of thing. The
Yeah,
RHS
okay.
is the number of permutations in general. The LHS
Okay.
is just like take k points, fix them, and then permute the rest.
Yeah, that won't work. The rest shouldn't have any fixed points, is also there.
Right. Okay.
So this can be, in fact, phrased as k into n choose k into dn minus k, where d is like the number of ways. That is a fair interpretation. But like, why would you want to do this? Like, this is a fair interpretation, no issues at all. But yeah, you would never want to do this. Is there a good way? I wouldn't give you the problem if there was no good way.
No. To compute that sum, the arrangement was that.
Yes, it is this sum, exactly. So you go towards this and then you do the sum.
Sure.
Yeah, not fully sure how to follow through with it, but like some picking special thing somehow probably is there. But other than that, I'll need more time.
Yeah, precisely that. So you just say permutation, comma, one fixed point. You consider such pairs. How many there are? Summation of k p of k. Like for every permutation, there are k choices if it has k fixed points. So there are this number of. Yeah.
Wait. Can you repeat? You're listing all the permutation comma fixed point pairs, right?
Fixed point of sigma, like sigma and a fixed point of sigma.
Yeah, and you're doing this for all fixed points, so overall permutations.
Overall permutations, sure. Not overall. Yeah. So that is k sigma. That is sigma kp of k, right? Because first you pick the permutation. If it has k fixed points, then you have k choices.
Yeah.
Okay. So kp of this is the answer. So for the fixed point, first you pick the fixed point instead. There are n ways to pick the first fixed point instead. And after you pick the fixed point, There are just n-1 things you have to rearrange. N-1 factor.
Sorry, I got a second. How did you reinterpret it then?
So earlier I was first picking the permutation and then picking the fixed point, right?
Right.
That was summation k p of k. So first I pick the fixed point.
Mm-hmm.
There are n options for that.
Mm-hmm.
Now there are n minus one
okay.
factorial permutations
yeah.
with that as a fixed point.
Got it.
Because you never want to do that. Why would you do that to yourself? Isn't that like painful and all?
Like in
D is very
contest,
ugly.
I mean, you have no other option in contest.
No, you do this every time. Don't do the problem instead.
Yeah, like this idea was quite intuitive.
Exactly. And okay, let me put it this way. If you don't do the problem, it's okay. But but if you do it this way, then you're very happy. And if you do it that way, okay, you get 7 points. Congratulations. Yay. What even are you going to do with those 7 points? Nobody remembers them.
Oh, yeah. Yeah, this is like quite big talk. Words.
What's the source, by the way?
Oh, I think 87 IMO, I think.
This is even a IO problem?
I think this is 87 IMO.
Yeah, it's okay. So this is quite old.
Yeah. Yeah, okay. This kind of problem won't appear in IMO anymore. Just because people will. I am assuming it's 1 or 4. Let me just quickly check. Like
That
even
was
then,
also
this.
a joke. P3 is also a joke, what Pranav said.
Okay.
No, I don't remember the problem.
Let's just check if I even know the source correctly. Yeah, it is P1. Okay. Is this clear?
Yes.
All right, awesome. So let's try a problem from Argentina. Where did I store this? Right. There are n cars. Numbered from 1 to n. And a row with n parking spots. Again numbered. No, because like every car belongs to some person, right? And because people are weird, they have favorite parking spots. So the owner of car I has some favorite parking spot, which we'll call AI. Okay.
There is exactly one favorite parking spot, or there can be
One. For everyone, there's some favorite. Like you and I can have different favorite spots, right?
And
The
same
car
people
I,
also.
yeah.
So each person has a different favorite parking spot, right?
No. We can have the same spots as favorite also,
Oh.
but we just have some favorite spots. Okay.
And
So,
there is exactly one favorite spot for each.
yes, exactly one. So
Yeah,
when your turn to park comes, you try to go to your favorite spot, okay? And if it is free, then you park. And if it isn't free, then you just go to whatever next spot is free and you park there. Okay.
Oh, so if like my favorite spot is AI and it's occupied, I go to like the next free spot. right?
No, you'll go to AI plus 1. AI, you'll go AI plus 1. If that
And
is occupied, you'll go to AI plus 2.
yeah, so the next free spot only, no?
Yeah, and you'll keep going till n. If even n is occupied, then you just leave. Then you're like, I don't like this car parking anymore. I'm going home.
I see.
Arey, think of it this way. Like you enter this car park from here, and you're like, this is my favorite spot. You reach there and you see, oh my god, this is occupied. You keep driving, okay, I have to park anyway. And you reach the end. You're like, oh my god, I don't have the effort, energy to go back. I'll just leave.
Yeah.
Cool.
Yes.
So, car one uh, parks, like car one comes in and tries to park. Then car two comes in and tries to park, and so on. Okay, this is your process. Now you need to tell me the number of lists A1, A2, AN such that everyone parks.
So there are totally n people with n cars.
Yes.
Wait, what is A1, A2 and all?
Oh, you need to tell me the number of lists A1 to AN
Okay.
such that everyone parks.
I'm just like completely. I'm not writing anything down. Just like a guess. So like a list is good if and only if for all j greater than I, aj is less than ai.
List is good
If for all j greater than I, aj is less than ai.
not necessarily.
Yeah, possibly not work. Like I'm just like completely going off. Like I'm not writing.
Right, right. You're saying that if that condition is true, then it will work, right?
Yeah.
But is it an if and only if condition?
Okay. Yeah, that's not what. That's the thing. Like, is it only if? No, it's if, right? Like if works,
Yes.
but not necessarily only if. Fair enough.
Yeah.
The cars are coming in the natural order, right? 1 to n.
Yeah. Yeah. 1 to n.
Okay.
Okay, is it true that if one person's so like car one is preferred spot is say I, or the next person's preferred spot should be I plus one or I minus one?
Not necessary. Not necessary. So what is the annoying condition here? Firstly, tell me that.
Because they can't go back after that preferred spot.
Exactly. So can you fix that somehow? Maybe like by counting something multiple times, but can you fix it?
What if we like do like a modern thing? Like you keep going. So like if n fails, then you just do one again.
Yes, that is something you can do. But isn't it a little bad just because it changes your condition completely?
Yeah, it gets too weak. Like then everyone can park for all condition for all sequences.
Yeah.
Okay.
Also, like, you only care if somebody leaves. If one person leaves, you're already having whatever you wanted, right?
Yeah.
Okay, good.
Could we do something with the number of times AI repeats? Like, is a repetition in AI? Each of those separately?
We don't want to do many cases. Okay. See, go on, Pranav.
Yeah, so we like first consider person I, and its favorite spot is like AI, and
Mhm.
there are like two possibilities I was thinking of. If AI is greater than I, then
Mhm.
it's fine, like you can
Okay.
park. And if it's less than I, then we consider like all the
Why? Just a question. Why, if AI greater than I, then you can park?
oh AI less than I, then
Uh,
because sorry AI less than I you can park, no, because there are only I minus one people who went before it, so even if they park you have more options, no, you can park.
no, that is saying n minus I is less than I. Like n minus I is less than AI.
Yeah, fine.
Okay, sure.
And if in the other case you like consider all the people like who went before it, so like the first I minus one people, and
Too much.
like
Too
it
much
becomes
cases.
case by case, yeah.
No, we'll not do cases. Like, sure, there will be cases, but there will be clean cases.
I see.
Like, it has to look like after seeing that, you should be like, oh, this is very nice. This is cute. Don't give me something that is.
Yeah.
This is a very pretty problem. Okay, so tell me what we are missing. The condition that somebody is leaving, right? That we are not able to encode well enough.
Yeah.
How do we encode that into the problem? No, 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 no. Equivalent, something equivalent to the problem. You shouldn't be losing out on information.
Add another n spot to the parking lot.
Why? Okay, you only need to care whether one person left. You don't need to care if many people are leaving.
Yeah, so what if we just add like one extra spot in the end?
Perfect. So now there are n plus one spots. Now the question is asking you, is the n plus one spot occupied or not?
Oh, right. If it gets occupied, that means our sequence. Oh, okay, right. If it gets occupied, then the sequence that like A1 to AN fails.
Yes.
Yeah, all fails.
Okay.
Yeah.
So now can you use a previous idea that you had?
Oh, we could like do a recursion at
No,
two.
no, no, no. That was not the
Uh,
previous idea.
oh, I was not there for like this is on me. I was not there for the previous idea. So I joined it now. But
No,
okay.
no, 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 no. You also had this idea. It's okay.
Oh. Okay.
Okay. Meenakshi, what was the issue that you were saying? That we
Uh,
were,
because they can't go back after like their favorite parking spot.
right. Now can you go back is the question.
You still can't go back, right? You just get another extra spot, so you don't need to leave.
Right. So the problem is, okay, so now if this car park is occupied and now you don't need to leave, now you can just re-enter because the point is this spot is already filled. It doesn't harm us. We just needed to know is this spot being filled or not.
That is so clever.
So repeat that again.
The question was, is this spot being filled or not? The spot is being filled. So you can re-enter. It's okay.
Oh, okay. Yes.
Like we just wanted to know, is this spot being filled? Yeah. Okay, cool. If the spot is not filled, then that's the thing we wanted to count. So nobody's re-entering. See, we wanted to count whether the spot is filled or not. So if nobody is re-entering, then this spot is never filled. And if this spot is filled, then I don't care if anybody is re-entering. Let them re-enter.
Yeah.
I was just asking whether the spot is filled or not. Okay. So now everyone can re-enter. So what is the issue now?
Yeah, like how do you sort of track back now to what you're?
Yes, perfect. So if I have the sequence A1, now it doesn't matter where you even enter from, for that matter. Like you're just saying your entry spot is AI now. Like the whole thing is now your just entry spot is AI for you.
Yeah, exactly.
Wait, how is entry spot AI?
I mean, you're not looking at the first AI minus one things, right? So you can just pretend your entry spot is AI.
Yeah.
And your parking spot, parking is a circular thing now.
Yeah. So after n+1, you can go back to first.
Yeah. So your thing is just like now, you can go back, and all you're saying is your entry spot is AI, and you can go to anything after it. And the question becomes, is this spot occupied or not?
Sure, but like, how are we achieving circularity? Like, what is even
No, this is just an interpretation.
This is just an interpretation. Now, what I'm asking you is how many ways of choosing AI
Right.
from 1 to n, which does not involve you ever using the parking spot n+1.
Right.
The primary idea of adding another parking spot. The question becomes equivalent to, is this parking spot occupied or not? That is the reason you do it.
But like counting that is still the same thing. No? How do you count it?
Yeah. Coming to it. Yeah, now they won't leave. So we have this extra restriction that I really don't like. We are saying that n+1th spot you can't choose as your favorite spot. I'll allow you to choose that. For now. We'll come back to it later.
But we
for
don't
now,
want it to get filled. Like
yeah. Like those cases are bad anyway, right? So we won't count them. Like if anybody's favorite parking spot is n+1, it's going to be bad.
Right.
But
So just n
an+1 is
minus one.
also allowed as a favorite spot.
What?
No, so is an+1? So what if an+1 is someone's a favorite parking spot? Is that allowed or what?
What do you mean an+1? There's no n+1. It's just an. Sorry, it's just parking spot n+1.
Yeah, I mean parking spot n+1. So if it's like so is it like counted as? Can it be like someone's favorite spot?
Yeah, doesn't matter, right? If it's anybody's favorite parking spot, they're going to end up on it. Like somebody's going to end up on it if it's anybody's favorite parking
But
spot.
won't that make someone having two favorite spots?
No. I'm saying like you can choose between 1 to n, or you can choose at n+1. But if you're choosing at n+1, I'm never going to count that case.
No,
Just
anyway,
because somebody is at
it will be
n+1.
filled.
Like the point is the yeah. So if anybody's favorite parking spot is n+1, that means either n+1 is filled, or when they go there, they fill it. So that is never my case. Like I'm only counting when n+1 is not filled. So it's okay for n+1 to be anybody's favorite parking spot.
Yeah.
Okay,
Like
so then we just take all the cases, like we'll just take all the possible cases for like all the possible lists, and then just subtract the ones that involve an n+1.
kind of. The point is like now it's a complete circle. It's a circle. The probability of one being left alone is the same as n+1 being left alone.
Wait, I don't get that.
like the at the end of the thing, exactly one thing is left, right?
Right.
So if one is left alone or n plus one is left alone, it's the same because it's a circle. I'm just saying you enter here and you go clockwise till you can.
Right. 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 Yeah. 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 Fair enough.
Yeah, yeah, symmetry. There's like no difference between n plus one. I could just say this is parking spot and you enter at a certain place and you go clockwise till you can. I don't need to give them a labeling, right?
Right. Then we just count cyclic permutations.
No, what permutations? So it's just like n plus, you have n plus one options for each of the n people. So n plus one to the n, but each has a favorite, like each spot being left alone has equal probability. So upon n plus one.
Right.
So the
Right.
answer is n plus one to the n minus one.
Oh, wait, how did you do this?
Each,
Calculate.
if, oh, just like every person has n plus one options.
Yes.
So n plus one to the n
But
ways.
favorite spots matter, no?
Yeah, your favorite spot you chose. So like whatever spot is left is has equal like it's equally possible that n plus one is left or one is left. There's no difference between them now.
Wait, can you repeat why we should divide it by n plus 1?
Oh, just because this is counting how many cases are, how many choices of favorite spot is there. But this also involves like one being left being the point which is not occupied, or two being the thing that is not occupied, or three being the thing that is not occupied.
Okay,
Right.
yeah.
So basically, like the cyclicity idea that now it's cyclic. But I'm on like a little uncomfortable with like how is it how is adding a new spot making the whole thing cyclic? Like how are they getting equivalent one and n plus
Yeah,
one?
because they can return now.
Yes, the point is, what am I asking you to count? I'm asking you to count. You
All
have
the
this,
lists that don't involve an n plus one.
all the lists that nobody sits at comes into n plus one.
Yeah.
Now, if anybody has favorite parking spot n plus, and I allow you to have favorite parking spot n plus one.
Right.
If anybody has favorite parking spot n plus one, like that means n plus one is occupied. So that's not a case we are calculating anyway.
Right. Yeah. Not just so like all lists that lead someone to an n plus one is what we're counting.
Yeah. And if we even make it circular, doesn't matter. We are still counting the list that n plus one is not occupied.
Right. Okay. Okay. Cool. That makes sense. That's nice.
But it's a circle now. And all I'm saying is you pick a spot that you want to enter from. And keep driving in a circle and sit wherever you can. So now, how many lists of favorite spots are there? A1 has n plus one choices. A2 has n plus one choices, and so on. So n plus one to the n choices of lists of favorite spots. And each spot has an equal chance. So n plus one to the n minus one.
I mean, how will you think
Humans
that?
cannot solve, but really?
No, this is not unreasonable. This is a decent problem.
Yeah. This question is not that hyped that humans cannot solve.
No. It's a tricky and it's a hard problem and it's very cool, but it's not that impossible or anything.
Yeah, but still, that adding seems very unreasonable at first.
Yeah, of course it is. It's not an easy
I think
problem.
there are many more problems which are way harder than this.
Yeah, why do we care? It's just like a pretty problem, and let's just admire that.
Yeah, exactly. But yeah, again, this was quite clever.
Yeah, for sure. Okay. Yeah, you can take 5 minutes to just digest this.
This was problem 6, 87.
I don't know. This is like from Argentina 97.
Oh, okay.
Where did you find these problems?
Oh, this was in Pablo Soberon. This problem.
Makes sense why you like the book.
Go on, this is just amazing, no?
Yeah. The IMO one was also in Pablo.
Uh, it must be like I knew the IMO one otherwise as well,
I see.
but it has to be in Pablo. Come on, like this problem I knew only from Pablo is the point.
I see.
Also, like all of this is like from the chapter which is functions.
Are there such problems in PRS also?
Uh, Problem solving strategies never use
No,
that.
no, no. Pranav Shriram, PRS.
Oh, Pranav Shriram has never used either. I just know it's good. Right, Argentina 97. All
Not
right.
visible on your side.
What's the name of the book?
Ah, what's the name of the book? Good
Like the
question.
author. The author. Just.
Oh, Pablo Bravo Sobron. And problem solving methods in combinatorics and approach to Olympiad problems. It's a brilliant book. I absolutely love it. And I
What's the
think it
name of
has
the
a,
book?
okay, I'll repeat. Problem solving methods in combinatorics and approach to Olympiad problems.
Oh,
I think it also has all solutions, which is like very nice, and hints. Like all exercises have hints and solutions, if I remember correctly. Yeah. And the entire book is like 185 pages. So like there's just like 100 pages of content and then 85 pages of solutions, I think. So it's very nice. Right. Yeah, I'll just do one thing on functions and then I'll conclude. Oh yeah. The thing is about that book, like because it's 100 pages and it covers very good content, the slope can be very high. Like it will start by defining something, use it in an elementary problem, use it in an national Olympiad. Suddenly you're doing IMO problems. So you shouldn't be like, oh my God, I'm not able to solve this hard problem. You're not supposed to. You just did a national Olympiad problem. You're not supposed to be able to solve IMO problems that fast. Take your time with it. Right. Okay. So I'll do one last problem. This is also from Pablo Sobron's book. This is on bijective functions. Just a small thing that I'm sharing this just because when I first saw it, I was like mind blown. Because at that point, I was just introduced to what even bijective functions are. Oh, I didn't know what bijective functions are till after my first RMO. After qualifying my first RMO, I didn't know what bijective is. So it's okay to not know these things. Right. All right. So you have an n by n grid. I'll actually give two problems and you can try whichever you like. This is the harder one, by the way. Just say.
Harder one to solve.
I'll see. I'm free till 9, so we can try both if Abhi doesn't kill me. Abhay, is that okay, by the way?
I mean, sure, I guess. I'm thinking about it. Yeah, go ahead. I mean,
Right, sorry. Uh, yeah, sorry. This is from OIM, which is, I think, the Mexican Olympiad. So you have an n by n grid, and initially each square has a lamp, okay, and every lamp is turned off. But besides every lamp, there is a switch, and if you press the switch of the lamp with the lamp in this box, what it does is very weird. Not only does it like switch the lamps of this box, but it also switches the entire row and the entire column, and this itself, of course. Okay. So now what we want to do is we want to switch on all lamps.
Repeat once again.
What it does is when you it not only switches on, but like if you press a lamp, it will turn it off. Like if it was on, it will turn it off. If it was on, it will switch it on. So just toggles. Yes. Thank you. Toggles every lamp in its row and the column. So now you have to find the minimum number such that you switch everything.
Wait, how many lamps are there?
Oh, in every box there's a lamp.
Okay, yeah.
Minimum number of like toggles you need, right?
Yes, minimum number of toggles. Yes.
And is it given, or we have to like think ourselves that for every and there exists a way to make them on?
Prove it. I mean, if you can find a minimum, if you can find a minimum number, I'm assuming you can do it.
Fine.
Also, just toggling everything switches everything on.
Very helpful, Atul. Very helpful, like always.
It's not that obvious.
It is not that obvious. Don't do that.
No, I guess what he said is that toggling all. Hello.
Hello. Yeah. Your voice got cut. They're all off in the beginning. Yes. Okay. Right. This is one
So what is
question
the final question?
Oh, minimum number of toggles to switch everything on.
Oh, so at first they're off, like default.
Yes, yes, yes.
Yeah.
Okay, this is first question. And the second question, do whichever you like. You have an m by n grid with mn coprime. Okay.
Just like a thing. In the first one, if n is odd, then just toggling an entire row works. Just like toggle every switch in the row and it'll work.
N odd.
Then just switching off, like just toggling an entire row is enough, I think. And I'm not sure if you can go lesser than that.
Can we go lesser than that? Anybody else?
Like every row will have to be toggled,
right? Why at least one thing in every row?
Like each time you toggle, you're just toggling a row once, and like you're toggling at most one in the column.
Yeah, but like
minus one toggles, you're not toggling at least one thing.
Yeah, how?
Like exclude the n-1 rows used, exclude the n-1 columns used. That's one square.
Yes, good. So just write all I index rows not used and all j in the index of the row not used and the index of the column not used, then I comma j can't have been. toggled.
When you're like switching on or off, you have to do it like one row at a time.
One toggle, just like on any squares, on any cell.
Okay.
That toggles the entire row and the entire column.
Oh, so it, both get like switched on at once.
Yeah, absolutely. Okay, second question.
But
You
I don't
have
understand that IJ argument.
I'm saying like there's some like when you're okay, just like consider all the indices of rows that you have toggled. Like if you like ith row you toggle, right? Like if you call a comma b you pressed, then I am considering you toggled the eighth row.
Yeah.
Okay, so I just like list out every row you have toggled.
Yes.
There's some row you haven't toggled I.
Yeah.
Similarly, there's some column that you haven't toggled j. Then I
Yes.
comma j you couldn't have it toggled ever because you didn't toggle anything in the row or in its column.
Oh, yeah.
Yes. So like this, you have m by n grid. These are m squares. These are n squares. Teacher, oh my god, like this gets progressively worse. It started at Rohan, then became RG, then it became RG sir, and now it's teacher.
I think teacher here doesn't refer to you.
Ah, it's their teacher. I see. That's like so much better. Thank you, Pranav.
Welcome.
Did I just end up making 10 and this 5? Of course I did.
5 and 10 are co-prime.
It's 11, okay? Don't lie. Right. So now you draw this diagonal. Okay. Find the number of squares that I intersected.
Is this supposed to be discussed?
You know the answer to this?
No,
Atul?
it's in promised application this year.
Wait, this is in promise. This is in what?
I think so.
This is from mathematical.
Yes, this came at the promise this year.
Okay, I can't say it then. Sorry. Amazing. They're now picking off problems from the most famous books. Interesting.
This was a really common problem, and I was amazed to see this.
Yeah, some others are also just told them.
Yeah, I knew they're mostly not original, but like the level of how famous it should be, I thought was a bit.
This question also came in like Technothlon from the past 2
But can we
years.
still do it anyway?
Yeah. No, I would rather not just because.
Oh yeah, it's
If-
like cheating. Yeah.
Yeah, because some people might end up using it. Like, okay, come on. This is not good if they're using this famous problems. But sure.
Okay, can we do another one instead?
Yeah. Like, let's just do the first problem, right? And Abhay will also be happier if we finish in 10, 15 minutes.
Yeah. Okay.
Okay, great. Yay. Let's try this one. Maybe promise is mostly for Americans, right? So they choose problems from non-American contests. Is that their only criteria? Right. Just a joke. Don't take it seriously. Please.
Yeah.
Right. Atul, your idea. Can you repeat? What were you saying in the beginning?
Wait, that's horribly unoptimal, right?
Yeah, that's unoptimal. But what was the idea?
Or toggle the entire
Wait,
board.
what is mean by optimal?
Oh, like minimal. Just like how many minimal number of steps you need to do.
Oh, okay.
Right. So Atul says toggle everything. N squared steps.
If we do everything, then won't okay. But what won't there be some stuff that are getting like switched off?
Yeah. The thing is, everything gets toggled 2n-1 times, right? You get n-1 toggles like this, n-1 toggles from here, and your own self. So you get toggled 2n-1 times, so you end up being on. Does it make sense? Sorry.
As
All
long
right.
as it's not a power of 2, just n works, right?
How?
If it's 2 times an odd number, just that odd number at the top and that odd number at the bottom, to the left and to the right.
How? Like you're doing here and here?
If it's 6 by 6, then three to the top right and 3 on the top bottom right, top left and bottom right. That one.
Top left.
Oh, okay, I'm
This.
completely wrong. I'm completely wrong.
Okay. Yeah.
I think we should start from one of the corners and do it diagonally, like each line.
Okay. If you toggle, let's say this and this.
It's a
Now this
square,
is
right? The grid is a square.
yes. But the thing is, if you just toggle this and this, then these have been toggled twice, so they're still off.
Oh.
Sorry, I'm rushing up. I'll end up rushing a bit just because I want to end by 45.
We just want to choose a subset of cells such that in everything's row and column there are odd number of things chosen.
Wow. Like, of course, that is what you want to do in some sense. But how do you even go about that, proving that?
No idea.
Exactly. Okay. Do we toggle anything twice? Like, do
No,
we
you might as well have not toggled.
exactly? So we press every switch exactly 0 or 1 times, right?
Why not 2? Oh, like because
No, odd number of times in general, right?
Yeah. I mean, 0 or 1, right? That's all you care about. If you're pressing 3 times, you might have as well pressed 1 time, right? Like, if you're pressing this switch 3 times, then you could have just pressed it once and the effect is the same. Okay. So everything is pressed either 0 or 1 times. So how many ways can we toggle the grid? Like, how many choices do you have of choosing things, ways to toggle?
2 per n square.
Perfect. You have 2 per n square ways of toggling. How many configurations are there?
2 per n square.
Ta-da-da-da.
Magic.
So what do you
What's
realize?
the configuration?
Oh, just like what things are on and what things are off. Just
Oh.
like 2.
Oh yeah, it's 2 to the power n square.
Yes. Okay, so these are equal. Now the point is, if we can show,
two toggles reach the same thing.
or you want to show that everything is achievable.
Yeah.
Surjective function from a set of equal size to another set has to be bijective.
Yeah.
So all you need to do is show us everything is achievable. So I toggle this entire column and this entire row.
It only toggles one thing.
Only toggles this place.
So everything is achievable. So n square is minimal.
So everything is achievable, precisely.
Wait, I didn't
Every
understand.
okay. So I say, see, this is let's say it's a function from A to B, where A is the set of things where you're toggling, like
Yeah.
the set of switches you're toggling, and B is the set of lamps that are on at the end.
Okay.
How many elements in A? 2 to the n square? Just because n square options and each you could have switched on or off.
Yeah.
B has 2 to the n square.
Yeah.
Now, if we show everything in B is achievable, then it's a bijective function just because it's surjective
Oh.
and sets are equal.
Oh, yeah, yeah, yeah.
And if we have shown that, so toggling all works. So that can be the only thing that works.
Yeah, okay.
So we just need to show that everything is achievable. So how do I show everything is achievable? I just need to show that any particular lamp can be switched on. If I can switch on just exactly one lamp, then I can switch on whatever lamps I want.
Wait, exactly. Yeah. So, but we can switch on any lamp. So, so exactly one lamp, like at. Wait, what do you mean by that?
Like if I can show that I can switch on this particular lamp, then I could have switched on any other lamp as well, right?
Yeah.
With a series of toggles. So if any set of lamps I want on, with some series of toggles, I can switch them on as well.
Okay. Yeah. Yeah. Okay.
But how to switch this on? I just toggle everything in its row and its column.
Oh. Yeah.
Yeah, and you're done. So n square.
Oh, that's so cool.
Yeah, it's very cool. Yeah. This is very different from your standard set of grid problems, so I don't know what to really tell you. Also, like, yeah, grid is a huge trope. You'll have to talk about. There are some graph theoretic ideas. You want to sometimes think of it as bipartite graphs, whatnot. I don't want to talk about it right now. Like, let's just enjoy today for some counting things.
Yes, yes.
All right, I'll stop screen sharing then.
Can we do one more?
I would have I just like I said 9 because I have to teach another thing at 9, and I realized that I haven't had food yet. So I can't right now. I can give you some problems though.
Oh no, it's fine. Yeah.
Right. Sure. The one you already have that I gave the problem about
The
uh,
diagonal one.
the ladder. Sorry, elevator. My God, ladder. Seriously.
Oh
Anyway,
yeah.
problems. So from IMO 98, there is this problem. I don't remember the exact statement, but the thing which has k by m greater than n minus 1 by 2n, whatever that problem is. Uh, then IMO 88, there's a very nice problem, which you'll see like odd a1 to a2n plus 1 sets. like I'm just writing this vaguely because you can figure it out just by going to the particular paper, which problem it is. Then
What does it say? A1, A2, all that?
there are like the problem will be talking about some sets A1 to A2 n plus 1.
Okay.
That problem.
Okay.
ECMO 2021 P5. Then okay, I'll give you a summation to try if you guys want. Summation k equals 0 to n minus 1 to the k n plus 1 choose k n plus n minus. It's written as n minus k, so I should write as n minus k for any m and n. Okay, is this good enough, or do you guys want more?
Is the last
Yeah,
one
it's,
using generating functions or like some
No,
argument?
no,
A nice combo argument exists.
of course. Why would I give you if there was nothing like that?
I see. Also, the first term is m plus 1 or n plus 1?
M plus 1, m.
M plus 1 c k and m plus n minus 1 m plus n minus k. And the second term is?
M plus n minus k n minus k.
I see.
Right, sorry for the handwriting. Right, okay, one last problem. This is Switzerland 2010. Village associations. I wanted to cover one more problem today, which was this problem that I will obviously not have time for. IMO 2004, Societies and Gangs. IMO ISL 2004. This is, I think, one of the favorite problems of Shara, I think. So, yes. Okay, good enough. Or do you guys want one more? One more, okay, sure. Let me find this one.
That's sure I like the ISL problem because he himself did something gangster in his university.
No, I hope not. I hope not. Right. Okay. Let f be a permutation. Is a permutation. Right? Yeah. Right. Right. Sorry, this is bad. Let S be a set with n elements. With n positive integers. And f is bijection. Okay. Prove that summation f to the I of I greater than 2n minus root 2 I belongs to S.
Is this summation? Okay.
I mean, f to the I is just f applied I times. No. All right. These problems. I'll stop presenting them.
Also, that summation wala problem है. The sum is till n or m.
The summation is still m or n? N. Oh, I'll just send the entire PDF of today.